Question 3, energy. A rider and bike with combined mass of 85 kgs climb 4.0 meters vertically in 3.0 seconds while biking up a track. Calculate the average power required. Cool. So this problem is an energy problem. Who would have thought? We are given a mass. We are given like a height or a distance, and we are also given a time. And the first question is asking us to find average power. Great. So as the rider starts, let's say at this height, and then climbs a height of 4 meters, they are gaining gravitational potential energy, right? Now, depending on how long it takes them to do that climb, they will exert more or less power, right? If they do it very fast, then they're pedaling really hard, they're outputting lots of power. If they take it in a lower gear, pedal a bit more slowly, they won't need as much power, but it will take them longer to get up the hill. So, let's have a look at our formula sheet first and see where we can find power. So power equals energy, or equals work done over time. So let's write that in first. So we know we're going to need work done over time, or energy over time. So what is the energy in this scenario? Well, since they're gaining height and they have a mass, they are gaining gravitational potential energy. And in our formula sheet, we can jog our memory. So EP equals mg delta H. So let's bring this down here. So just listing out the formulas we're going to need. Alright, and I'll just clean that up a little bit. The beauty of a digital pen. Alright, so we need to find the energy, the gravitational potential energy, and then we can substitute that into our equation for the power. So EP will equal the mass, 85 kgs, times gravity, 9.81. Well, actually, formula book says use 9.8, but, let's be more accurate. Times change in height, 4.0 meters. So if we compute that, 85 times 9.81 times 4 gives 3,335 joules. So that's the gain in gravitational potential energy. Now we can substitute that into our power equation. So power would equal that energy out of time, 3.0 seconds. So we can hit divide by 3 to give 1,111.8. And what are the units for power? I know you're laughing right now. Yes, they are watts. Awesome. We could, or rather should, use how many? 2 or 3 sig figs for this problem, but either or. Right. So this question is actually, surprisingly, a merit question. So if you got the correct gravitational potential energy achieved, if you then use that to work out the correct power, merit. just while we're here, another way you could have worked out that energy is to use the work done. So just as an aside, remember from level 1, work done equals force times distance. So the force in this case comes from the weight force, which acts down. So the weight force is m times g, and then the distance in that vertical direction would be the 4 meters. So it's actually equivalent to the potential energy formula in this scenario. Alright, now the rider bikes over a 4 meter long bridge and stops 3 meters from the end. So I think a diagram down here, yep. So they're just 1 meter into the bridge. The bridge has a uniform mass of 700 kilograms, and the combined mass of the rider and the bike is 85 kilograms. State the conditions required for the bridge to be in equilibrium. So, equilibrium. That just means the bridge isn't rotating about any pivot points, and it's not accelerating in any direction. And I guess in this case would be assuming it's static, so it's not moving at all. So the two conditions for static equilibrium, number 1, no net forces. So that's your gravity, your friction, your support forces, right? When you add them all up in all directions, they should sum to 0. But in level 2, we also learnt about torques, which is a force applied at a distance, which causes something to rotate. So for it to be in equilibrium, there must also be no net torques. And that is an achieved question. So static equilibrium, there are no net forces and there are no net torques. You could have also said balanced forces and balanced torques. Right, same meaning. Cool. Alright, but those conditions are very important, especially when it comes to questions like this last one that we'll get to, where we analyze a problem. We need to use both of those conditions. Alright, getting ahead of myself though. Question C. Draw labeled arrows to represent all the forces acting on the bridge. Right, so imagine you are the bridge. You are 700 kilograms with a uniformly distributed mass. What does that mean? That means you have a weight force. Right, you're pretty heavy. Now where would that weight force be? Would it be over here? Somewhere in the middle? On the other side? Would it be going up? Would it be going down? So if it's uniformly distributed, the center of mass would be in the center of the bridge, the geometric center. Weight force will be acting downwards. Yeah, like so. So that is the weight force of the bridge. Alright, what other forces are acting on the bridge? Well, you have a cyclist just riding over you. So their weight force will be acting downwards on you as well, assuming their center of mass is, somewhere in the middle there of the cyclist. We could put an arrow here. And how would their weight force compare to your weight force? Would it be greater, the same, or less? So they have a combined mass of 85 kgs, whereas you have 700 kgs, so quite a lot less. And to show that, we will draw the arrow, the length of the arrow, as being less. Yeah. It doesn't need to be perfectly to scale, just as long as you get the idea across. Okay. Now, a good question to ask at this point: are the forces balanced? No, right? At the moment, we only have downwards forces, which means this bridge is accelerating towards me right now. If I was, I don't know, swimming in the river, somewhere down here, right? But for it to be in equilibrium, we said we need the forces to be balanced. So what are the other forces involved here? Right at the ends, at these pivot points, A and B, they will be providing support forces. And they will act upwards. Now, would they be equal, or would one provide more support than the other? A really good thing you can do if you have, I don't know, a 30 centimeter ruler nearby, is you balance it on your index fingers, and then you get a family member or a friend to just push it in the middle, see how it feels, and then push it to one side, see how it feels. And hopefully you'll feel, as they push towards one of your fingers, that finger experiences more of the force. So in this case, the support force at A will be greater than the support force at B. And we show that by drawing the arrow at A a bit longer than at B. Right? Doesn't need to be perfect, but that looks good. Cool. And if we got that far, we actually got a merit. Well done. If you didn't get the relative sizes or the relative lengths correct, for example, at A and B, then it's only unachieved. Alright, I guess while we're here, let's just check that we've drawn our arrows to the correct length. Remember we said for equilibrium, there needs to be no net forces. So if I add up my vertical forces, they should be equal and opposite. I'm a little bit off. Okay, I don't know. Merit minus for me, but pretty close considering. Oh, come back. Please hold. Back. Alright. Awesome. Alright, so that's quite a generous merit question if you considered the relative lengths. Now the last question, the big one. Calculate the values of all the forces acting on the bridge. Great. Well, we can get two pretty easily, namely the weight forces. A few more steps to get those support forces. Right, we'll do an equilibrium analysis using the forces and the torques. Both of those equilibrium conditions. Great, so let's start with the easy ones because we can. Before that, I'm just going to label each of my forces. So I'll do FB, force of the bike, FB, force of the bridge. No, dilemma. What should we do? I know. F bike, F bridge. Right? Don't be afraid to, if the word's short, to use the full word in the subscript, because when you read it back, you can actually look at your work during the calculation. So yeah, but these ones I'll just label FA and FB. Cool. So we have our forces labeled. So F bike, we know that's a weight force of the bike, so it'll be the mass of the bike times G, and the mass of the bike was 85 times G, 85, oh, not divide, times 9.8, 833, or 834 newtons. Now F bridge equals the mass of the bridge times G, which was I think 700 times 9.81. 700 times 9.81, 6867 newtons. Awesome. Looking good. What is next? So this is where we need to use the second equilibrium condition, right? No net torques, but to get there we need to work out the torques, or they're sometimes called moments. So you could pick any pivot point, so we could pick about point A. I'll pick about point B. However, I do encourage you to try about point A to see that you get the same results, right? If you don't, well, double check your work. So let's go about point B. So I'll say finding torques about point B, right? Just to make it clear. So just a reminder, torque is force times distance, where the force F is perpendicular to that moment arm, that torque arm D. So in this case, all of the forces are perpendicular to the bridge, so we don't need to take like cosine or sine of any angles, right, to get the components. So at least that makes it a little bit easier for us. So from point B, let's start with the force at B. Now, actually, before that, let's split it up into clockwise and anti-clockwise directions. You can combine this into one step, but I'll just split it up. So what I mean by clockwise and anti-clockwise is at point B, both of the weight forces are pushing it down, which is going to want to make the bridge spin anti-clockwise, right? Whereas the support force at A is pushing up and is going to want to make it spin clockwise. So those are the opposing torques. So let's just say torque anti-clockwise about B, so tau ACW anti-clockwise about B. We said that was due to the weight forces. So F bike times the distance the bike is away from B, which is 3 meters, plus F bridge times the distance the bridge is from B, which is 2 meters, right? Exactly halfway along the bridge. And yeah, we could have put in the values for F bridge and F bike in one step, but let's just do it in two. So F bike, we said 834. F bridge 6867. And if we compute that, plus 6867 times 2, 16,236, 16,236, and torque is in Newton meters. So that was the anti-clockwise direction. Let's do the clockwise direction about B. Now the force at B, since it is at B, right, it's a distance of 0 from the point, so it doesn't contribute to the torque. So the only other force acting up is FA, which is 4 meters away. So FA times 4 meters, well, do we know what FA is? No, we don't, right? So we'll just leave that as 4FA. Cool. Right, now we can use the second equilibrium condition, right, which says that the clockwise torque must equal the anti-clockwise torque. So clockwise or anti-clockwise must equal clockwise. So we can equate those two highlighted portions. And then in this case we'll divide both sides by 4 to solve for FA. So 16,236 divided by 4, 4,059 newtons for force. Awesome. So let's label that up here, 4,059 newtons. Oh, one more to go. The force at B. Now you could do all of this again, except about point A, right, and you will get the force at B. However, we can use the first condition, right, balanced forces, instead, right? It's a bit easier. So what that says is the upward force, FA plus FB, must equal the downward force, F bike plus F bridge. So F net must be 0. So FA plus FB will equal F bike plus F bridge. Again, that's just saying the forces acting up must be equal and opposite to the forces acting down for this to be in equilibrium. Now we can substitute in what we know. Well, we just worked out FA. Don't know what FB is. F bike plus F bridge, we have worked that out. F bike 834, F bridge 6867. So we can subtract 4,059. So FB equals 834 plus 6867 minus 4,059. Can compute that on our calculator. 6867 minus 4059 to give 3,642 newtons. Whew, that was a big one. So let's recap that. But if you find both of the support forces, so FA and FB, that is excellent. If you just found one, merit. If you just found one of the torques, that would be achieved. Right, but let's recap that. So the question was to calculate the values of all forces acting on the bridge. So we started with the weight forces, F bike and F bridge, mass times gravity. We then picked a point, a pivot, so either A or B. I chose B, but you should try A as well. And we found the torques. We then used the condition that the torques in the clockwise direction must equal the torques in the anti-clockwise direction. And we used that to solve for the support force at A. Right, at this stage, we know the support force at A, F bike and F bridge. And since there's only one unknown, namely FB, we can use the first condition of equilibrium, that the net force must be 0. Right, so we said the vertical forces, FA plus FB, the upward forces equal the downward forces. Substituted in our values and solved for FB. Awesome. So at this stage, you got excellence. Well done. Pat yourself on the back. Go to your exam, make your teacher proud, and have a great day. See ya.